You know that incredible, almost magical thing a CT scanner does? It takes a bunch of simple, fuzzy X-ray shadows and somehow builds this perfect, crystal clear 3D map of our insides. How on earth does it do that? Well, it's not magic, it's actually a brilliant piece of mathematics.
And hey, if you've ever tried to wrap your head around it and felt totally lost, you are not alone. This whole process is called reconstruction. And yeah, it's complex, but it's also one of the most brilliant parts of medical imaging. Today, we're going to pull back the curtain and demystify it together.
So, it all boils down to this one big question. How in the world do we get from this bizarre wavy pattern of lines?
This thing is called a synogram. It's the raw data the scanner collects. Think of it like a scrapbook of every single X-ray shadow of an object taken from hundreds of different angles all around you.
And then, through some kind of mathematical wizardry, turn it into this. I mean, look at that. An image so clear you can see every individual structure inside a patient.
That journey from the wavy mess to that crystal clear slice, that's the magic of reconstruction. And that is exactly what we are going to break down right now. Let's start at the beginning.
Okay, so the first step in solving this whole puzzle is to collect all the clues. And in the world of CT scans, these clues have a specific name. They're called projections.
Think about it like this. If you wanted to understand the exact shape of a new building, you wouldn't just take one picture from the front, right? No way. You'd walk all the way around it, taking pictures from every single angle. A projection is basically one of those pictures, a 2D X-ray shadow. The CT scanner just spins around you, collecting hundreds of these projections to build a complete picture.
And you know, this whole idea isn't even new. The math behind it was actually proven to be possible way back in 1917. But it took decades of technological progress, a Nobel Prize, and a ton of engineering to turn that theory into the life-saving tools we have today. And honestly, the biggest leaps in quality have all happened just in the last decade or so.
Okay, so now we have hundreds of these shadow pictures. The most intuitive, common sense first step to put them together is just to layer them on top of each other, right? That technique is called back projection. You can think of it as making a really blurry first draft of the final image.
Let's make this super simple for a second. Imagine our object isn't a complex organ, but just a single tiny point. When we take an X-ray of it, from one angle, the projection we get is just a simple spike in the data. That's the shadow of the point.
So here's how the computer starts to rebuild. It takes that spike of data and paints it back across an empty canvas, smearing it along the exact path the X-ray took. The catch is, the computer doesn't know where on that path the point was, so it just distributes the shadow evenly along the entire line.
We just repeat this process for every single angle. Now all the lines cross at the right spot, which is great. But because we've smeared each projection, the final image isn't a sharp point. It's this blurry star shape. We've found the location, but the image is way too fuzzy to be useful. So how do we get rid of that blur?
Well, for decades, the answer to that blurriness was an elegant mathematical trick called filtered back projection, or FBP for short. This was the workhorse algorithm that made modern CT possible.
So how does it work? It's pretty clever.
Before back projecting, the computer applies a filter. This filter adds what you can think of as negative wings on either side of our data spike. When these filtered projections are layered, the positive spikes add up to create the point, while those negative wings perfectly cancel out all the surrounding blur. It's genius.
Now, if the negative wings idea is a bit abstract, think of it this way. A prism can take white light and split it into a rainbow of different color frequencies. Well, a mathematical tool does pretty much the same thing for our projection data. It turns out all that blur is caused by too much low-frequency data. The filter simply tones down those low frequencies before the algorithm recombines everything, giving us a much sharper final image.
This method was fast, it was effective, and it absolutely dominated CT imaging for years. It was the gold standard. But as doctors pushed to use lower and lower radiation doses to protect patients, a critical weakness of FBP started to show. It's very, very sensitive to noise.
And that challenge, getting high-quality images with less radiation, led to a whole new revolution in CT, a smarter, more powerful technique called iterative reconstruction, or IR.
So how does IR build a better picture? Well, while FPP is a fast, one-shot calculation, IR is a completely different approach. It's a complex, multi-step process. And yeah, it's more computationally intensive, but its ability to produce clean, high-quality images from low-dose scans is nothing short of revolutionary.
And the impact is just staggering. Clinical studies have shown that using iterative reconstruction allows for a reduction in patient radiation dose of anywhere from 23 to 76%, all while maintaining or even improving the diagnostic quality of the final image.
You see, instead of a single calculation, IR uses the sophisticated guess and check loop. First, the computer makes a rough guess of the image. Then it simulates a CT scan of its own guess to create fake projections. It compares those fake projections to the actual ones from the patient. Finally, it notes the difference, corrects its guess, and runs the whole loop again, getting closer to a perfect image with each iteration. This is a fundamental shift, from a simple mathematical recipe to an intelligent process that is actively hunting for the best possible image.
Iterative reconstruction completely changed the game, making CT scans safer than ever before. But technology doesn't stand still. The next great leap forward is already here, and it's powered by artificial intelligence.
So let's just quickly recap this whole evolution. We started with 2D shadows. Back projection gave us a blurry first draft. Filtered back projection sharpened that image for decades. Then, to make scans safer, iterative reconstruction introduced a smart guess and check system. And that brings us to the next frontier, AI.
Right now, deep learning models are being trained on huge libraries of CT scans. These AI networks are learning to remove noise and reconstruct images with incredible speed and accuracy, essentially supercharging the iterative process. But the key insight here is that AI isn't just cleaning up the image, it's learning what human anatomy is supposed to look like. This allows it to reconstruct amazing images from far less data than ever before, pushing radiation doses even lower while making the whole process virtually instant.
This all brings us to a final, fascinating question. As we go from simple shadows to filtered math to intelligent loops, and now to AI that can learn the very structure of the human body, are we on the cusp of a new era in medicine? A future where we can get a perfect, instantaneous look inside any patient with a radiation dose so low it poses almost no risk at all? The journey of reconstruction suggests that future may be closer than we think.